Hello guys, welcome to another calculus video. Today we're going to be checking out this cool problem which will give us a double integral over a sphere radius r, which is going to be really cool. So basically what this problem is we're trying to figure out what forces are acting upon an object which is inside a sphere. So we'll just imagine that this is the Earth and it's going to have a radius r and a uniform density delta. And then this object is going to have a mass, lowercase m, and we are going to try to calculate how much force is pulling this object into the center. Because if you think about it, when an object is in the very center of the Earth, since it has equal amounts of mass on every side, it won't actually have much force being applied on it. However, we also know that once an object is outside of the Earth, the further away it gets, there's less and less force. So that implies that in some point from the center to the outside, there will be some sort of maximum point where there's the most force possible. So without any further ado, let's go ahead and jump into the problem. So we have our sphere, and we have our center of our sphere and this object. Now the first thing I want to point out is that we'll only be considering the distance from the center. And the reason for that is because if we orient the sphere so that the object is in the center on one of the planes and it's just a certain distance up on the other axis, then everything on the left and right and front and back of it will kind of cancel because there will be even amounts of mass in every direction except for one direction, which is the up and down. So we'll imagine that our object is kind of in the center when we look from the top. This would be the top view, but if we look from the side, it'll be somewhere up here, right? So that's the first thing we have to cover. And the second thing is, how exactly are we going to integrate it? So in order to integrate this, what we're going to have to do is we're going to have to figure out some way to integrate over the entire sphere and sum up all the individual masses and their forces. Now the easiest way that I figured out how to do this is by using a little disk. And the reason for this, or not a disk, a ring. So if I have a ring of radius lowercase r, the area is given, and the width here is dr, the area is given by 2 pi r dr. And the reason for this is because the inner radius and the outer radius are so close to each other that there's virtually no difference, so we can just multiply the circumference by the width, which is dr. And imagine, if you will, we have our sphere. This would be the center line, and this is the center, and our object is somewhere here. Now, anywhere, if I were to draw a small disk right here, for example, up here or down here, you could imagine from the top view, this would look like a disk like this, or a disk like this. Every point on that disk actually enacts the same net force on the object. And that's just because, as we said before, we're only going to consider the force that's pulling this object up or down, because everything else will cancel. And every object on every point on this ring is the same distance in terms of the radius. It's the radius is the same everywhere on the ring, so that distance is the same, and also they're the same height. So what we're going to do is we're going to take these small rings, we're going to give them, I'm going to try to draw a 3D image here and it's going to suck, just wait. So we have our little rings, right? We're going to give them a height of dh. Oh dear, I'm sorry about this image, but can you imagine it's just like a little ring and it's going to have a diameter of r, a width of dr, and a height of dh. And so what we're going to do is we're going to integrate the force that's on these rings. First we're going to integrate r going all the way out from 0 all the way out to the edge, and then we're going to integrate h going all the way from the bottom of the sphere all the way to the top. And so what's that going to look like? Well, first of all, for our outer integral, we can say that h is going to go from negative r to r. But for r, it's a little bit more complicated because on each individual disk here, it can't go all the way out to r because, for example, if we're looking at this disk and we integrate it all the way out to r, now we're integrating on a cylinder rather than a sphere. So we'll just use the fact that this sphere has a radius r. So this max r just means that that's the maximum value that our r will attain, because our r is kind of going from the center here, and it's going to go out here. So this would be like our max r. And then plus h squared. So for any h, we're going to have a different maximum value of r. And if we just solve for the maximum value of r here, it's going to be the square root of r squared minus h squared. So that means when we integrate, r is going to go from 0 to square root r squared minus h squared. So let's do that real quick. And now we just have to figure out what goes in our integrand. And of course, all that is the force exerted by any one of these. So of course, force equals g m over r squared. I apologize for having similar variables here, but this r just represents the distance between the objects. And so we can substitute g and m in here already. For the other mass, of course, we're only talking about the mass of one of these rings. And so that's just going to be the volume of the ring times delta. And of course, the volume, as we said, is going to be 2 pi r, which is the area, times dh. Or 2 pi r dr times dh. And of course, we have to add delta for our density. Next, we have to talk about the force. So the total force, right, we're going to use r squared. And of course, the distance, thinking about our little ring here, it's just going to be the height squared plus the radius here squared and the square root of that, right? Because the distance is this one, which is just this and then this, right? So d equals the square root of h squared plus r squared, which is pretty easy because then d squared is just h squared plus r squared. But of course, we're not going from the center of the sphere. We're doing from the height where the object is to where the ring is. So that means instead of h squared, we're going to have h minus h0 squared, where h0 is the starting height of this object. So all of this is going to be squared, so we can just write it as h minus h0 squared plus r squared, right? Now, the only thing that's missing is this will give us all of the force exerted upon the object. But we only want to look at the force that's exerted in a vertical manner, right? So I'm going to draw my sphere again. We have our ring here, and we said that this is our total force. And we calculated that. But this force is, of course, made of two components of force, one that's pushing this way, one that's pushing this way. And we don't need to worry about this one, right? We only need to worry about the this length here. And so what we need to do is multiply by this length and divide by the total distance, because it's kind of like multiplying by the sine of the angle, except in this case we don't have the angle. So we're going to end up kind of only taking out the part that's exerting in a vertical manner, which is this component of the force, which is what we want. So we're going to multiply by that distance, which is just h minus h0. Now you could also argue it's h0 minus h, but that's just going to change the sign of our whole thing. And so I'm going to leave it as h minus h0, and at the end we'll just flip the sign if we have to, because obviously we know that the force is being exerted towards the center. And so we're multiplying by h minus h0, and we're going to have to divide by the distance, which is square root h minus h0 squared plus r squared. So we'll just write a little 3/2 here. And I'm going to go ahead and reorganize our integral here. I'll let delta g m pi delta gm is just going to equal k, and we'll remember that. And so give me a moment and I'll reorganize our integral. All right, and we have our integral all set up. All that we need to do is start integrating it. So the first integral that we're going to do is the inner integral with respect to r. And so what I'm going to do here is, since we have this 2r in the top and the r squared in the bottom, I'm just going to set u equals r squared, right? And so this together will be du, and so our integral is going to be. I'm going to change this to r squared minus h squared without the square root, because now we're integrating with respect to r squared. And actually, I'll just let du equal this whole thing, because then du over dr will still be the same. and then we could just immediately integrate. So the integral of u to the negative 3/2 du is going to equal u to the negative 1/2, and then we'll divide by, so negative 2 u to the negative 1/2. So I'll just let that negative 2 come out. Actually, I did forget about the bounds here, so I will put this as, I'm going to change this back to what it was before. So I'm going to leave it as that because I don't want to mess with this right here. And so we're going to end up with negative 2k h minus h0 times u plus h minus h0 squared to the negative 1/2, evaluated at r squared minus h squared and 0 dh. And let's move on to the next slide. Alright, so if we plug in both of these bounds here, we're going to end up with negative 2k to row of negative r to r of h minus h0 over, okay, so r squared minus h squared, we're going to end up with r squared minus h squared plus h minus h0 squared to the 1/2. And then we're going to subtract h minus h0 over h minus h0 squared to the 1/2 dh. And so if you notice this is actually going to cancel, but we have to remember that something squared times that same thing to the 1/2, or something squared, the square root of something squared is just the absolute value of that original thing. And so we can't actually fully simplify that. We'll have to leave it as absolute value. So a really cool thing that I want to mention here is that the derivative of the absolute value of x equals what's called the sine function, or the signum sometimes. And this is just kind of, it's -1 if x is negative, it's 0 or undefined. It doesn't really matter, depends on who you ask. I mean, it's really undefined. But you could define it as 0 and that wouldn't cause any problems because it's only at one point. So it's undefined at 0, and for positive values it returns 1. And this signum function is actually equal to x over absolute value of x. So if we want to integrate this, we actually only, the integral of this is just going to be the absolute value of h minus h0. So let's go ahead and do that. So when we go ahead and plug in r and negative r in here, we're going to get 2k absolute value of r minus h0 minus 2k absolute value of r negative r minus h0, which is just r plus h0. Okay, so in order to integrate this nasty part, we're actually, since we have an h in here and an h out here, we're going to actually have to separate this a little bit. So r squared minus h squared plus h squared minus 2h h0 plus h0 squared. And so this is going to cancel. And we're just going to end up with negative 2h h0 plus h0 squared plus r squared. And so I'm going to write that in. And what I'm going to do, just to make this a little bit more simple, is I'm going to set h to negative h, or I guess you could say like u is negative h, and then I'll change the name of u back to u. So what's going to happen is we're going to end up with a negative dh. These bounds are going to flip, and so those are going to cancel with each other. So we can keep the bounds the same and just flip the sign of h everywhere. And so that's going to make this disappear. And it's going to make everything inside here become negative. So I'm just going to factor out that negative sign. And so we'll end up with plus, plus. All right. That makes everything a little bit easier. Now the problem with this is we're actually going to have to do a few tricky things here. So what I'm going to do here in order to do this is I'm going to multiply and divide by h0. So we're going to put this out here. we're going to do 2h h0 plus 2h0 squared. Then on the inside, I'm going to add, oh, this is an h0 right here, sorry about that. I'm going to add plus r squared plus h squared, h0 squared, and then I'm going to subtract r squared minus h0 squared, right? And so the reason for all of this is now we can split this into two integrals. We end up with k over h0, integral from negative r to r, 2h h0 plus r squared plus h0 squared, plus that same thing all to the 1/2 dh, right? And then we're going to end up with another integral where it's going to be this, this, and this, and so we're just going to end up with h0 squared minus r squared all over 2h h0 plus r squared plus h0 squared to the 1/2 dh. And so for this first one, since we have the same thing in the top and bottom, that thing will always be positive because even when h is really negative because of the r squared and the h0 squared, it's going to be okay. So we're going to just cancel that on the top and bottom, and we don't need to worry about absolute values for this. So we're just going to end up with this to the 1/2, and we can erase the rest. Okay. So in order to integrate this one, I just want to be really careful here. The integral of u to the 1/2 du equals u to the 3/2 times 2/3, right? So first, because of the chain rule, we're going to be dividing by 2h0. So we're going to be k over 2h0, and then we're going to multiply by 2/3. So that's going to get rid of this, and we're going to just have a 3 there. And then we're going to have this whole thing, which is called b, I don't know, b to the 3/2, evaluated at r and negative r. For this other integral, we're going to have something very similar. We'll just factor out these constants. In this case, we have something to the negative 1/2, right? So what we're going to do is we're going to end up with, when we use the chain rule, we're going to end up with this 2h0 squared on the bottom because that's what's multiplying by h. And then we are going to, the integral of u to the negative 1/2 du is going to be u to the 1/2 times 2. So we're going to multiply by 2 again, and so that's going to cancel with this right here. This 2 will go away. And then we're just going to end up with b to the 1/2 r negative r. Okay, so let's go ahead and plug these in. So we're going to end up with k over 3h0. Now, when h equals r, we're going to end up with r squared plus 2h0r plus h0 squared, which is just the same thing as r plus h0 squared. And so when we raise r plus h0 all squared to the 3/2 power, we have that square root again that's going to cancel, and so we're just going to end up with the absolute value of r plus h0 cubed, right? Or we can put the cubed outside because 3 is an odd number, so I'm going to fix this up real quick. And similarly, when h is negative r, we're going to end up with r squared minus 2h0r plus h0 squared, and so that's going to be pretty much the same thing. It's just going to be r minus h0 all to the 3rd power, and I'm going to put the parentheses here. And then for the second integral, we're going to have the same thing, except it's just not cubed anymore. So we're going to end up with plus k h0 squared minus r squared over h0 squared. All right, and so we're going to end up with this. I believe the bit that came from the absolute value integral was 2k times absolute value of r minus h0 minus absolute value of r plus h0. So overall, this should be our answer, I believe. I'm trying to see if I'm missing anything here. Okay, I'm sorry, I just noticed this when I'm looking over my work. When I did the chain rule, I forgot to divide by h0 with this one, so this is h0 squared and this is h0 squared, and that should give us the right units everywhere. Okay, now we have a lot of absolute values here, but we can simplify a lot of things. So first off, the first thing we want to do is we want to consider if the object is outside of the Earth, because we already know what the force should be if the object is outside of the Earth. So let's go ahead and simplify this. Now, when the object is outside of the Earth, first off, r plus h0 is going to be positive because h plus 0 will be greater than r. And similarly, r minus h0, h0 will be greater than r, so it'll just end up being h0 minus r, right? So we're going to end up with k over 3 h0 squared, times r cubed plus 3 h0 r squared plus 3 h0 squared r plus h0 cubed. And as we said before, we're subtracting h0 minus r cubed. So h0 cubed minus 3r h0 squared plus 3r squared h0 minus r cubed. And if you notice here, the sign on this h0, these are going to cancel, right? And then because of the sign, oh, I should mention there's still a negative sign here. Because of the sign on this and on this, these are going to cancel. And so we're just going to end up with k over 3 r cubed plus 6 r h0 squared, 2r cubed, all over h0 squared. All right? Then from this next part, we're going to have plus k h0 squared, or actually I'll write this as 1 minus r squared over h0 squared. As we said before, this is just going to be r plus h0, and this one is going to be h0 minus r. So we're going to have, so these are going to cancel, and we'll just end up with 2r right here. And next, for this last part, we're going to have 2k, r minus h0 is going to end up being h0 minus r, and then we're going to be minus r minus h0. So this is going to cancel, and we'll just end up with negative 2k, negative 4kr, I guess. So if we expand everything out, 2k over 3 r cubed over h0 squared plus 2k r, right, plus 2kr minus 2k r cubed over h0 squared minus 4kr. So here, all of this is going to cancel, right? And then all we're going to end up with is negative, so this would be 6/3, so 2/3 minus 6/3 is negative 4/3 r cubed over h0 squared times k. And with some quick simplification, you're going to see how magical this is. So remember we said k is pi g m delta, right? So minus 4/3, and I'm going to take this r cubed, and I'm going to take this pi, and I'm going to take the delta, and this is just negative the mass of the Earth, right? So, and then all that's left over is where we have the g and the m over h0 squared. And so we're going to end up with negative g m over h0 squared. And this is exactly what we should get, naturally, because when the object is outside of the Earth essentially acts like it acts as if its center of mass is its center of gravity, and we can just use the basic law for gravity, which is negative gmm over h0 squared. So as you can see, this is great for me because it's confirmation that I did my integral right after I don't know how many minutes of doing this integral, but that's good. But that's not really the answer that we're looking for. Now this obviously does verify that this equation for gravity works for a celestial object, but we still want to look at what happens when the object is inside the Earth, and that's the really interesting part. So we're going to use this equation, and we're going to assume now that h0 is less than r. Alright, so now when h0 is less than r, we're going to end up with something a little bit different. So we're going to have our first term, k over 3, I'm using this line, just to remind you, k over 3 h0 squared. This first one's going to remain the same because it's still positive. Now this one, since h0 is less than r, we are just going to, the absolute value is just going to stay the same. It's just going to be r minus h0 cubed. And I'm going to go ahead and simplify this now so that I can save space. So as you can see, this r is going to cancel. This h0 squared r is going to cancel. And the rest of this will just end up adding together. And so that's what's going to be for that first term. Now for the next term, we're going to have plus k 1 minus r squared over h0 squared. And it's just going to be r plus h0 minus r minus h0. And so those r's are going to cancel, and we're just going to end up with 2h0, I think, right? Does that make sense? Yeah. Then for this last term, very similar thing, plus 2k. R minus h0 is just r minus h0. Then we're going to do minus r plus h0. And so we're just going to end up with, I believe, alright, so r minus h0 minus r minus h0. And so it's just going to be negative 2h0. So if we multiply all this out, this first part is going to be 2k r squared plus 2/3 k h0 plus 2k h0 minus, oh, this first term, I'm sorry, should have an h0 on the bottom, and so we're going to end up with minus 2k r squared over h0 on this from this term, and then minus 4k h0. So as you can see, this will cancel with this beautifully. And then this 2 and this 4 will just end up with a negative 2 right here. So I'll go ahead and write that, because 2 minus 4 is negative 2. And so overall, we're going to end up with negative 4/3 k h0, or negative 4 pi over 3 delta g m h0. Right? Yes. So I think this is a pretty interesting result because, as you can see, this is actually linear with respect to h0. So you start at the center of the Earth. If we were to graph the force with respect to h0, it would increase linearly like this until a certain point. When it touches the outside of the Earth, it starts dropping off with an inverse quadratic curve like that, which I think is super interesting because this is the first time that I've really seen a real piecewise function that shows up in physics. And just to ensure that this point is the same, if you go ahead and plug in h0 equals r into here, you'll get negative 4/3 pi delta gmr. And you will get the same thing if you plug it into the other formula that we got, which is just negative gmm over h0 squared. You will actually get the same exact thing. So I just think that's super interesting, that when you're inside of the Earth, or inside of actually any spherical object, the force experienced is proportional to the distance from the center. So yeah, that's it for this video. We just had a really cool double integral, some cool physical applications, and of course this amazing discovery right here, which I mean just blew my mind the first time I discovered it. So anyway, thanks for watching. If you watched through the whole video, wow, that is surprising because this is really long. And yeah, I'll see you next time. Hope you enjoyed.